And I once had a letter from a lawyer who said, roughly speaking, evolution can't be true because a species is defined as members can always interbreed with each other. And you can't imagine that there was a time when child generation was incapable of breeding with the previous generation.
Here, Neil deGrasse Tyson is talking about how our definitions, tidy and convenient, can mislead us when we apply them to a messy, continuous world. We love boxes with crisp edges. This is a species, that is not. But biology, like most of nature, isn't built from factory parts. It's carved by time, geography, and chance. And no word we invent can force a clean line where the universe has drawn a gradient. Let's face the worry head on. If members of a species can interbreed, then where in the chain from ancestors to descendants do you draw the line that says, now a new species has appeared? Across adjacent generations, individuals are usually compatible when they overlap in space and time. So how could you ever end up with non-interbreeding groups? Here's the twist. Neighbor-to-neighbor compatibility doesn't guarantee compatibility between the distant ends of the chain. Consider a ring shaped by geography. Greenish warblers spread around the Himalayan plateau in two arcs, north and south. Each local population can mate with the next population along the arc. But by the time those arcs meet again in Siberia, the endpoint populations show strong behavioral and genetic differences and rarely pair, with only limited hybridization. What happened? No magic generation, just accumulation of song changes, plumage cues, and genetic tweaks, small steps in each neighborhood, adding up to a big difference around the ring. This isn't a trick of language. It's what you get when evolution operates on a landscape over time, a spectrum that loops back on itself, where continuity along the path coexists with incompatibility at the ends. Now, raise the stakes. That ring can be drawn not only in space, but in time. Organisms transform across generations the way a language shifts across centuries. Nobody woke up one morning speaking Spanish instead of Latin. Villages spoke mutually intelligible dialects. The dialects drifted, and across long distances and long years, the chain stretched until the endpoints couldn't understand each other. Biology does the same across evolutionary time. In most cases, you won't find a single generation where offspring can't mate with their parents when they overlap, but you'll find ancient ancestors and modern descendants so altered they might as well be strangers. But there are exceptions that happen fast. In plants, chromosome doubling, polyploidy, can produce an offspring that's instantly incompatible with its parents. Wheat is a famous mosaic of such events. In the 20th century, botanists watched new goat's beard species arise in North America through hybridization and chromosome duplication. In one or two steps, a lineage is reproductively cut off. So yes, sometimes nature drops a boundary like a drawbridge. More often, though, it weaves a fence gradual enough that you can't say which picket made it a fence at all. Here's another case study that changes the way you think about boundaries. Lake Victoria's cichlid fish formed hundreds of species in just tens of thousands of years, an eye blink in geologic time. Many of these fish diverged not because they couldn't physically interbreed, but because females developed preferences for specific colors and shapes under certain lighting conditions. Change the water clarity, say by runoff that clouds the lake, and those visual cues vanish. Suddenly, the species barriers can erode, hybrids appear, and the family tree blurs. The lesson is unsettling and liberating. Reproductive isolation isn't a single switch. It's a dashboard of dials. Behavior, genes, ecology, nudged by environment and chance. This is why scientists don't cling to one definition of species like it's the Ten Commandments. Depending on what you need to know, you might group by shared ancestry, by ecological niche, by consistent diagnostic traits, or by reproductive compatibility. Each definition is a lens. Swap lenses, and you see a different, valid aspect of the same living continuum. The failure isn't in nature when the definitions collide. It's in us when we expect one lens to do the work of all. But let's not let the language problem distract us from the mechanics. The engine of speciation is the accumulation of differences that block gene flow. They can be genetic, mutations that disrupt chromosome pairing, or changes in timing of breeding seasons. They can be behavioral. New songs, new dances. They can be ecological. One group shifts to a new food source or habitat, experiencing different pressures. The key is separation. Physical barriers, like mountains, or functional barriers, like a new mating preference, that keep gene pools from blending back together. Left apart long enough, the gene pools diverge until the ends of that time-lapse chain, if you could bring them together, no longer mesh. And that raises a bigger point about how science works. We build categories to make predictions, not to imprison reality. Astronomers classify galaxies as spirals or ellipticals, yet galaxies morph under gravity in mergers. Chemists organize elements in a periodic table, yet isotopes smear the neat boxes. Biologists name species, but evolution keeps the lines moving. The map needs borders. The territory does not. Here's the payoff for embracing that discomfort. When we let go of the demand for a single, perfect cutoff, we ask better questions. Instead of, which exact generation became a new species, we ask, what factors are currently restricting gene flow between these populations? How strong are they? How quickly are they changing? Those are measurable, testable, useful. They help conservationists decide where to protect habitats, how to preserve not just species as names, but the evolutionary processes that generate biodiversity. They help us understand our own story, too. A braided history with Neanderthals and Denisovans, gene flow that didn't fit the tidy textbook diagrams and yet leaves a trace in our genomes today. So the next time your mind demands a hard boundary, remember the warbler's circuit around the mountains, the fish that split by preference and then rejoined when the water changed, the plants that leap a chromosome rung in a single generation. Nature is generous with transitions. We're the ones who insist on edges. If you're willing to trade certainty for understanding, to replace a bright line with a measured gradient, evolution stops looking like a paradox and starts looking like what it is, a process that builds difference from small steps and sometimes from swift leaps, without ever needing a moment when a child can't meet a parent halfway. That shift, from demanding perfect definitions to studying the forces at work, isn't just a semantic upgrade. It's a change in perspective that aligns our minds with how the universe actually operates, by degrees, by interactions, by time. And once you see it there, in the living world, you begin to notice it everywhere. Like if this was interesting and hit the subscribe for more.